Imagine digging deep into the earth and finding not just fossils of ancient animals, but traces of a city. Except the rocks around it are 100 million years old. That's the unsettling idea behind what scientists call the Silurian Hypothesis. It's not a claim that there was an ancient civilization before us, but a serious scientific question. If an industrial society had risen and fallen long before humans, would we even know it today? The strange truth is that almost everything humans build, our cities, machines, and even our plastics, has an expiration date when viewed through the lens of deep geological time. Plate tectonics recycles the crust, erosion wipes landscapes clean, and the fossil record itself is painfully incomplete. Out of the billions of species that have ever lived, the overwhelming majority left no trace at all. So the odds of finding direct evidence of a pre-human civilization, if one ever existed, are far slimmer than most people realise. Yet we also know that our own impact on the planet is leaving chemical and geological fingerprints that could be detectable millions of years into the future. Carbon isotope anomalies, synthetic compounds, and strange mineral deposits may one day serve as markers of our brief moment in Earth's story. So here's the question. If we can leave such traces, could something else have left them long ago? And have we simply misread them as natural events? The idea that humans might not be the first advanced civilization to live on Earth is provocative because it challenges something we usually take for granted. That history is a straight line leading up to us. When we look back through textbooks, the timeline feels orderly. Life begins simple, grows more complex, and after hundreds of millions of years, humans arrive with fire, language, and technology. That story is comforting because it makes us feel unique and inevitable, as if all of evolution was aiming toward us. But the Silurian hypothesis interrupts that narrative. It asks us to think about whether civilizations could have appeared before and vanished so completely that we would never know unless we looked in just the right way. This matters for more than curiosity. On one level, it's about humility. If Earth did host an industrial species millions of years before us, it would mean we are not as exceptional as we like to believe. Intelligence may not be a one-time accident, but something that can evolve, thrive, and then vanish, only to appear again later. On another level, the question is practical, because it forces scientists to ask what traces civilizations really leave behind, and how long those traces survive. That isn't just about the distant past. It also tells us what legacy humanity itself might leave. If the human story ended tomorrow, what would remain in 10 million years? Would a future species find unmistakable signs of us? Or would the rocks fold our entire existence into the same categories of natural warming events and extinction pulses that already fill the fossil record? There's a second reason the question matters. It forces us to rethink how we search for life beyond Earth. Right now, astrobiology looks for two broad categories of evidence: biosignatures, like atmospheric oxygen or methane that suggest life is present, and technosignatures, like radio signals or pollutants that suggest an intelligent civilization is altering its environment. But if a civilization only lasts for a few thousand years, and we happen to look millions of years after it's gone, those obvious signals would no longer be there. By asking whether we could even detect an ancient civilization on our own planet, scientists are sharpening the tools needed to search for civilizations that may have come and gone on exoplanets. In that sense, the Silurian hypothesis isn't really about Earth's past as much as it is about learning how to look for evidence of intelligence across cosmic timescales. The importance of this thought experiment also lies in how it reframes extinction. Most of the time when we hear about extinction, we think of dinosaurs, mammoths, or Ice Age animals. But civilizations can go extinct too. A technological species might rise, dominate the planet for a geological blink of an eye, and then vanish completely. If that can happen once, it could happen again. That possibility forces us to think about our own survival differently. We often act as though our civilization is permanent, or at least on a long trajectory toward expansion into space. But if there were civilizations before us that collapsed, then the question becomes, are we walking the same path? If Earth is a repeating stage for civilizations, then we are just one act in a much longer play. What also makes this hypothesis powerful is that it asks a deceptively simple question. What would be left after millions of years? At first, the answer seems obvious. We would leave buildings, tools, satellites, and plastic waste everywhere. But when you stretch the timescale, most of those things fade quickly, Skyscrapers collapse within centuries, bridges rust and fall apart, and plastics degrade under heat and pressure until they disappear into chemical traces. Even something as seemingly indestructible as a nuclear reactor would not survive unrecognizable after 10 million years. What lasts longest are not the artifacts themselves, but the indirect effects. Changes in the atmosphere, unusual layers in the rock, odd isotopes in the sediments. That realization changes how we see the past. It means that if another species had an industrial age before us, we wouldn't find their cities or machines. We would only find subtle fingerprints buried in the rocks, and even those might be easy to mistake for natural processes. Another reason the Silurian hypothesis matters is because it separates serious scientific curiosity from pseudoscience. For decades, fringe claims about lost ancient civilizations have been tied to things like out-of-place artifacts or myths of Atlantis. Most scientists dismiss those ideas because the evidence never holds up. But Frank and Schmidt's approach was different. They didn't claim that there was a pre-human civilization. They only asked whether the geologic record is reliable enough to rule one out. That distinction is crucial. It moves the conversation from the realm of fantasy into a structured scientific framework, where the question becomes testable in principle. Even if the answer is almost certainly, no, there wasn't one, the process of asking forces us to understand Earth's history better. There's also a cultural side to why this matters. Humans are fascinated by stories of forgotten worlds, myths of lost empires, hidden knowledge, and civilizations erased by catastrophe appear in cultures around the world. These stories reveal something deep about how we see time. We don't like the idea of absolute beginnings. We want to imagine that someone was here before us, that we're part of a much longer lineage of intelligence. The Silurian hypothesis taps into that curiosity, but grounds it in science instead of myth. It allows us to explore the same fascination while sticking to what we know about geology, biology, and chemistry. Finally, the question matters because of what it says about the fragility of knowledge. Our entire recorded history fits into about 5,000 years, and our industrial age into just 2 centuries. That is a blink compared to Earth's 4.5 billion years. If all of human civilization can rise in that tiny sliver of time, then it is at least imaginable that something else could have done the same long before us. And if we cannot rule that out with complete confidence, it humbles us. It reminds us that we are temporary, that the planet is older and more powerful than we are, and that whatever traces we leave might someday be as ambiguous as the signals we now puzzle over from the deep past. So the Silurian hypothesis matters not because it proves that we had predecessors, but because it forces us to think harder about what it means to leave a mark, what it means to endure, and what kind of planet we are actually living on. It's not just a playful idea, it's a mirror, showing us how narrow our slice of history really is. The phrase Silurian hypothesis sounds dramatic, but its origin is more playful than mysterious. In 2018, 2 scientists, astrophysicist Adam Frank and NASA climatologist Gavin Schmidt, published a paper that asked a surprisingly simple question. Would it be possible to detect evidence of an industrial civilization in the geological record if it had existed millions of years before humans? They weren't conspiracy theorists or fringe writers. Both were respected researchers who had spent years studying climate systems, planetary science, and the long-term future of civilizations. Their goal wasn't to argue that there actually was such a civilization, but to use the idea as a thought experiment to sharpen how we look for signs of intelligence, both on Earth and on other planets. The name itself came from the science fiction. In the British TV show Doctor Who, the Silurians were a race of reptilian beings said to have lived on Earth long before humans. They retreated underground and eventually re-emerged, creating tension with humanity. Frank and Schmidt borrowed the term with a wink, knowing it would catch attention. But they were very clear that this was not a claim about lizard people or hidden empires. It was simply a question. If an industrial species had once existed and then disappeared, would we even notice millions of years later? Part of what motivated their work was the realization that our own footprint on Earth is more fragile than most people think. Human industrial society has only existed for about 2 centuries. If it collapsed tomorrow, most of our structures would vanish within tens of thousands of years. Skyscrapers would fall, steel would rust, concrete would crumble, and entire cities would eventually be buried or eroded away. After a few million years, only scattered hints would remain, and even those might be difficult to interpret. Frank and Schmidt realized that if our own civilization is so temporary, then we should not be too confident in assuming that no one else ever left their mark before us. They also wanted to connect this question to astrobiology, the study of life in the universe. If civilizations tend to be short-lived and their traces hard to detect, then searching for technosignatures on other planets becomes even trickier. It means that when we look at an exoplanet's atmosphere or geology, we need to consider whether what looks like a natural fluctuation could actually be the residue of an earlier industrial society. Earth, as the only planet we can study up close, becomes the testing ground for this line of reasoning. If we can't rule out ancient civilizations here with total certainty, then we have to be cautious about drawing conclusions elsewhere. The paper laid out possible markers we could search for. Instead of looking for fossilized cities or tools which are almost impossible to survive deep time, they focused on indirect evidence, unusual isotopes, chemical signatures, sedimentary anomalies, and patterns in climate change. They compared these with known natural events, like the Paleocene-Eocene thermal maximum 56 million years ago, when a huge release of carbon warmed the planet by several degrees. Was that purely natural? Or could something industrial have caused it? Almost certainly natural, they admitted. But the fact that the signal looks similar to what we are currently producing means the question is scientifically meaningful. In other words, the Silurian hypothesis began as a way to remind us that the planet's history is long, evidence is fragile, and our assumptions about being the first intelligent species may rest on shakier ground than we realize. The point was not to suggest secret civilizations or to undermine the scientific consensus on human origins, but to broaden the scope of how we think about civilizations in time. Even if no one came before us, the hypothesis is useful because it forces us to consider what it would take to notice if they had. The timing of their work also mattered. Around the same period, scientists were increasingly talking about the Anthropocene, a proposed geological epoch defined by human activity. Our burning of fossil fuels, creation of plastics, and release of artificial chemicals are leaving signals in the Earth's sediments that future geologists will be able to identify. By tying the Silurian hypothesis to this discussion, Frank and Schmidt highlighted how narrow the Anthropocene really is. If our footprint is detectable, then perhaps other footprints could exist too. If not, then maybe we are fooling ourselves about how permanent our own signals will be. Either way, it reframes our sense of time and makes us think differently about what it means to be the first. So the origin of the Silurian hypothesis is less about hidden history and more about perspective. It's a lens that lets us look at our civilization as just one chapter in a book that spans billions of years. And by asking whether there could have been earlier chapters we missed, it makes us see both the fragility of our existence and the difficulty of detecting intelligence, no matter when or where it arises. To understand why the Silurian hypothesis even makes sense to ask, we have to place ourselves against the full timescale of Earth's history. Our planet is about 4.5 billion years old, and for most of that time, it has been able to support life in some form. Liquid water has been present for at least 4 billion years, and there is evidence that life began astonishingly early, perhaps within a few 100 million years, after Earth cooled enough for oceans to form. That means that for nearly the entire age of the planet, there has been at least microbial life thriving on it. But complex life is a more recent story. For billions of years, Earth was dominated by single-celled organisms. Multicellular animals didn't appear until about 600 million years ago, during the Ediacaran period. Soon after came the Cambrian explosion, around 540 million years ago, when most major animal body plans suddenly appear in the fossil record. From then on, the planet was home to an ever-changing cast of complex species: trilobites, armoured fish, giant insects, dinosaurs, and eventually mammals. That stretch of hundreds of millions of years raises an obvious question. In all that time, could another intelligent species have arisen? We tend to think intelligence is rare, but we also know evolution works through experimentation, trying out countless forms of life. The timeline is long enough that the possibility doesn't sound absurd at first glance. Still, let's frame this carefully. Humans have existed as a species for about 300,000 years. The first stone tools go back 2.5 million years, made by early hominins. Agriculture and written history appeared only about 10,000 years ago, and the Industrial Revolution began just 200 years ago. Compared to Earth's timeline, the human story is not even a blink. It's a fraction of a second on a clock that runs for billions of years. If you compressed Earth's history into a single day, humans wouldn't appear until less than a minute before midnight, and the industrial age would be only a heartbeat. When you see the timeline this way, the idea that humans must be the first seems less obvious. After all, why couldn't there have been an earlier rise of intelligence during one of the many other warm, stable periods Earth has gone through? Dinosaurs dominated the planet for over 150 million years, far longer than mammals have existed. Could some lineage of them have developed higher intelligence, built tools, or even started down an industrial path? Probably not, based on what we know of their fossils and brain structures, but the sheer time scale invites the question. Another important factor is that Earth's habitability hasn't been constant. There have been multiple mass extinction events. The Permian-Triassic extinction, about 252 million years ago, wiped out around 90% of species. The Cretaceous-Paleogene extinction, 66 million years ago, famously ended the dinosaurs and cleared the way for mammals to dominate. In between, there were long stretches of stability where ecosystems flourished for tens of millions of years. If intelligence takes a few million years to develop, there were plenty of windows of opportunity for it to happen more than once. However, the fossil record complicates things. Fossilization is rare. Most species that have ever lived left no trace at all. Even among those that did fossilize, we only have a partial and biased sample. Soft-bodied animals rarely fossilize, and environments like rainforests or mountains are terrible at preserving remains. Entire lineages could rise and vanish without leaving any obvious evidence. When you stretch that uncertainty across hundreds of millions of years, it becomes easier to see why scientists like Frank and Schmidt thought the question was worth asking. If a civilization lasted only a few 100,000 years, a generous guess, it might be as invisible in the rock record as most species already are. The scale of deep time also makes us rethink permanence. Humans tend to think of our world as fixed, continents in familiar shapes, climates relatively stable, oceans in the same places. But over geological time, continents drift, mountains rise and erode, oceans open and close. The Atlantic Ocean, for example, is only about 200 million years old. It didn't even exist when dinosaurs first appeared. If an industrial civilization had built cities on a continent that later sank beneath an ocean or was subducted into the mantle, its physical traces would be erased almost entirely. This is why Earth's long habitability makes the Silurian hypothesis so intriguing. The conditions for life and potentially even intelligence have existed many times over. Yet the physical processes of the planet, erosion, volcanism, plate tectonics, relentlessly destroy surface evidence as the clock ticks forward. That creates a strange paradox. The longer the timeline for possible civilizations, the less likely we are to find direct traces of them. There's also a biological angle to consider. Intelligence is not an inevitable outcome of evolution. Dinosaurs thrived for 150 million years without producing anything we would call civilization. Crocodiles have been around for over 200 million years and remain largely unchanged. But then in only a few million years, humans went from simple tool use to rocket launches. Intelligence may be rare, but when it happens, change can be astonishingly fast. That combination, a long timeline with scattered bursts of rapid adaptation, makes it hard to completely rule out that something similar could have happened before us. So when we ask how long Earth has been habitable, we're not just setting a stage for life in general, we're framing the possibility space for civilizations. If Earth has hosted stable ecosystems for hundreds of millions of years, then the idea that one and only one intelligent species has ever emerged starts to feel like an assumption rather than a certainty. The Silurian hypothesis doesn't argue that there was a civilization before us, but it points out that the timeline is long enough, the processes of evidence destruction are efficient enough, and the limits of our fossil record are narrow enough that we should at least ask the question seriously. When people first hear the idea of a pre-human civilization, the natural instinct is to think we'd have found it by now. After all, our world is covered in layers of fossils, sediments, and preserved clues about the past. If an advanced species built cities millions of years ago, surely we'd have stumbled across the ruins somewhere, right? The uncomfortable reality is that Earth is relentless at erasing its own history. Over the course of millions of years, almost nothing built on the surface is safe. The main reason for this is plate tectonics. Earth's crust is not a fixed shell. It's broken into moving plates that grind, collide, and slide past one another. At the edges of these plates, entire sections of crust get dragged downward into the mantle in a process called subduction. Ocean floors, for example, are constantly being recycled. The oldest oceanic crust anywhere on Earth is only about 200 million years old. That sounds ancient compared to human history, but it's less than 5% of Earth's total age. If you built an empire on land that later became seafloor, every trace of it would have been swallowed back into the planet long ago. Erosion is another silent destroyer. Wind, rain, ice, and rivers grind down landscapes continuously. Cities exposed at the surface don't last long. In just a few centuries, without maintenance, concrete breaks apart and steel corrodes. Within tens of thousands of years, forests or deserts reclaim the land. Within a few million years, those traces are not just buried, but often ground to dust. Even massive structures we think of as permanent, like the Great Pyramids or Mount Rushmore, would be unrecognizable after a few million years, if they survived at all. Volcanism adds another layer of erasure. Lava flows bury terrain beneath hundreds of meters of rock. Ash blankets regions and compresses into stone. Over deep time, volcanic resurfacing can completely overwrite whatever was there before. When you combine this with erosion and tectonics, the picture becomes clear. The geological record is more like a palimpsest, a recycled manuscript where the old writings scraped away and overwritten again and again. The fossil record itself is notoriously incomplete, and this is critical to the Silurian Hypothesis. Fossilization requires a very specific set of conditions: rapid burial, protection from scavengers, and the right chemical environment to preserve bones or shells. Even then, most fossils are fragmentary. Soft tissues almost never survive. Entire species can come and go without leaving a single, recognizable fossil behind. We know this because when new fossil beds are discovered, they often completely change our understanding of whole groups of animals. The fact that we have no fossils of a particular intelligent species isn't proof they never existed. It only tells us we haven't found them, and that they may never have fossilized in the first place. Geologists often talk about the completeness problem. Imagine trying to reconstruct a 1,000-page novel when only 5 random pages survived. That's the reality of trying to reconstruct 600 million years of animal life from fossils. Most of what we know comes from tiny, scattered fragments, often concentrated in special environments like river deltas or ancient seabeds. Vast stretches of history are represented by nothing more than a few mineralized shells or scraps of bone. If a civilization existed and lasted only a short geological time, say a few 100,000 years, its traces could easily fall into the blank spaces of the record. And then there is metamorphism, the process that transforms rocks under heat and pressure. Sediments that contain fossils or chemical traces can later be buried deep enough that they recrystallize into new types of rock. This wipes out fine details and often destroys subtle chemical signals. After hundreds of millions of years, the odds of a delicate signature surviving untouched are low. Even when we do find preserved events, they can be ambiguous. A sudden layer of carbon in the rocks might mean widespread wildfires, volcanic eruptions, or massive climate change. It could also, in theory, reflect industrial burning of fossil fuels. Distinguishing between natural and artificial causes becomes extremely difficult when all you have is a thin chemical smear in a layer of rock. All of this highlights a key point. Geological time is merciless to surface-level evidence. Civilizations, no matter how advanced, would leave only indirect footprints after millions of years. Their cities, machines, and monuments would crumble, subduct, or erode. What remains are the chemical signatures, isotope ratios, or unusual layers that tell us something happened here. But not necessarily what. From the perspective of human timescales, it feels absurd that something so grand could vanish without a trace. But from the perspective of Earth's 4.5 billion years, it's not just possible, it's inevitable. Almost everything vanishes. Species, mountains, oceans, even entire continents are temporary features. That's why scientists like Frank and Schmidt emphasize the importance of subtle signals. If you want to detect civilizations in deep time, you can't expect to find fossilized skyscrapers. You have to look for the fingerprints left behind in the chemistry of rocks, and the layering of sediments. And that's where the Silurian hypothesis pushes us to think differently. It doesn't suggest hidden ruins are waiting to be found in caves or deserts. Instead, it forces us to recognize that if an industrial society did rise and fall in the distant past, its only surviving legacy might be buried in geological anomalies that we already study, but interpret as purely natural. The harsh reality of geological time is that absence of evidence is not necessarily evidence of absence. It might simply mean that time itself has done its work of erasure. If an industrial civilization did rise and fall long before humans, what kinds of traces would it realistically leave behind? The Silurian hypothesis answers this by shifting focus away from physical artifacts like buildings or machines and towards subtle signals that could survive the immense pressures of geological time. Instead of ruins, we'd be looking for fingerprints etched into the chemistry of rocks, the composition of sediments, and the isotopes trapped within ancient layers of the Earth. The most obvious category is geochemical anomalies. Every time we burn fossil fuels, we alter the balance of carbon isotopes in the atmosphere. Plants preferentially take in lighter carbon isotopes, like carbon-12 during photosynthesis, which means that coal, oil, and natural gas are enriched in that isotope. When we burn them, the atmosphere and oceans shift toward an unusual carbon-12 to carbon-13 ratio. Future geologists will see that as a sharp spike in the rock record, an unmistakable signal of massive carbon release. If another civilization had also tapped into fossil fuels, we might expect to see similar isotope anomalies in layers millions of years old. But carbon is not the only element that civilizations could leave behind. Synthetic compounds are another potential clue. Humans have created chemicals that don't occur naturally, like PCBs, CFCs, and certain persistent pesticides. These substances can linger for centuries or millennia, and some could, in theory, leave detectable residues in sediments for far longer. If an ancient industrial society produced their own synthetic chemicals, traces might still exist as odd molecular fossils, or at least as unusual disruptions in the chemical composition of rocks. Then there's the question of metals. Industrial societies process and concentrate metals in ways nature doesn't. Aluminum, for example, is abundant in Earth's crust but almost never found in pure, metallic form. It requires large amounts of energy to refine from ore. Humans produce millions of tons of refined aluminum every year, and even if most corrodes, some of it might end up deeply buried in sediments. Other unusual concentrations of rare earth elements or alloys could be a telltale sign as well. If geologists found a layer of rock with strangely refined metals, out of line with natural processes, it would raise serious questions. Plastics are another striking marker. Today we produce hundreds of millions of tons annually, and much of it ends up in the oceans. Over time, plastics break down into microplastics that settle into sediments. Already scientists have identified plastic particles embedded in rocks, creating what some call plastiglomerate. In the far future, these plastic-rich layers may persist as thin bands marking the Anthropocene. If another civilization used synthetic polymers, we might expect similar markers. The challenge, of course, is that plastics degrade under heat and pressure. Over tens of millions of years, their survival is uncertain. But unusual residues, like odd distributions of carbon-hydrogen chains or microscopic fragments fused into sediments, could persist long after the plastic itself is gone. Nuclear activity also leaves fingerprints. Human nuclear testing and power generation have created isotopes like plutonium-244 and curium-247 that do not occur naturally in detectable quantities. These isotopes have half-lives long enough to survive for millions of years in tiny amounts. If another civilization harnessed nuclear energy, we might expect unusual radioactive anomalies in the rock record, distinct from natural uranium or thorium deposits. Even without synthetic materials, civilizations could leave behind distinctive sedimentary patterns. Industrial farming, deforestation, and urbanization alter erosion rates and soil deposition. Already, humans are changing the distribution of sediments worldwide, funneling more material into rivers and deltas than natural processes would alone. Over long spans of time, this creates distinct stratigraphic signals, unusual layers of silt or chemically altered soils that don't match background trends. An earlier civilization might have reshaped landscapes in similar ways, leaving behind strange, localized deposits. Some scientists also consider the possibility of technofossils. These aren't fossils of actual machines, but geological features produced by technology. For instance, concrete can harden into a rock-like material that may survive burial. Bricks, ceramics, and glass could also persist under the right conditions. While most would break down, a small fraction could become indistinguishable from natural stones, except for their unusual chemical composition. Detecting these would be extremely challenging, but not impossible. Finally, there's the indirect evidence in climate records. Human activity is driving rapid warming and altering the chemical balance of the oceans. Mass extinction events are likely to follow if current trends continue. A similar sudden spike in warming, paired with unusual geochemical signals, could suggest industrial activity rather than natural causes. In fact, this is one of the most provocative aspects of the Silurian hypothesis. Earth's past already contains events that look eerily similar to what we're doing now. If we're not careful, our own signal might be nearly indistinguishable from certain natural catastrophes, raising the possibility that we've already misread ancient traces. In short, if a pre-human civilization did exist, we wouldn't expect to find their skyscrapers or spacecraft. We would expect to find chemical oddities, strange isotopes, odd sedimentary deposits, and maybe rare artifacts of processed materials. The hunt would be for subtle deviations from what nature alone could produce. That makes the task both fascinating and frustrating, because natural processes are messy, and distinguishing civilization from catastrophe is far from straightforward. If there is one signal that civilizations almost inevitably leave behind, it is carbon. Industrial societies rely on energy, and the easiest and most concentrated source of energy available on Earth is fossil fuels, coal, oil, and natural gas. When we burn them, we're not just releasing carbon dioxide into the atmosphere in vast amounts. We're also leaving behind a very specific chemical signature that becomes locked into sediments and rocks. This is one of the clearest ways future geologists will know that we existed, and it's also one of the first places we would look if we were trying to detect a civilization long before our own. To see how this works, we need to think about isotopes. Carbon comes in several isotopes, but the two most important for this discussion are carbon-12 and carbon-13. Living things tend to prefer carbon-12 because its slightly lighter atomic weight makes it easier for biological processes to use. Fossil fuels are made of ancient organic material, so they are particularly enriched in carbon-12. When we burn them, the carbon dioxide we release into the atmosphere shifts the global ratio of carbon-12 to carbon-13 in a noticeable way. This change doesn't just stay in the air, it gets absorbed into the oceans, taken up by new plants, and eventually buried in sediments. Over time, those sediments turn into rock, locking in the isotopic anomaly. Already we can see this in our own time. Geologists call it the Suez effect, named after Hans Suess, who first identified it in the mid-20th century. The balance of carbon isotopes in the atmosphere and oceans today is drifting downward in a way that cannot be explained by natural processes alone. Future geologists studying rocks from this period will see that dip clearly, marking the Anthropocene as a distinct chapter in Earth's history. But here's the interesting part. When scientists look back at the ancient record, they sometimes find similar carbon isotope excursions, sharp shifts that indicate a sudden release of carbon into the atmosphere. One of the most famous examples is the Paleocene-Eocene thermal maximum, or PETM, about 56 million years ago. During this event, global temperatures rose by 5 to 8 degrees Celsius. Ocean chemistry shifted dramatically, and many species went extinct. The trigger was a massive release of carbon, which shows up in the rock record as a huge carbon isotope anomaly. Was it caused by volcanic activity, destabilized methane hydrates, or some other natural event? Almost certainly yes. But if you were a geologist millions of years from now, looking back at our time, you might see a very similar signal and wonder whether it was natural or industrial. That's exactly why Frank and Schmidt brought up the Silurian hypothesis. Our own footprint looks eerily like some of the mysterious events already buried in the rocks. Another layer of complexity is that carbon anomalies don't happen in isolation. When you dump large amounts of carbon dioxide into the atmosphere, it acidifies the oceans, disrupts ecosystems, and alters sedimentation patterns. Coral reefs bleach and collapse. Marine organisms with calcium carbonate shells struggle to survive. and extinction cascades ripple across ecosystems. These effects also leave their mark in the fossil record, often as sudden die-offs or gaps in biodiversity. If another industrial species had burned fossil fuels, we might expect to see both the isotope anomaly and an associated extinction pulse. The difficulty, of course, is that natural events, like volcanic traps releasing carbon dioxide, can cause the exact same pattern. That's why the signal is so ambiguous. There's also the matter of timescale. Humans have burned through fossil fuels in just a couple of centuries, an incredibly short burst of activity by geological standards. If another civilization had done the same millions of years ago, its signal would also appear as a brief spike in the rocks, a thin layer compared to the vast stacks of sediment deposited before and after. Detecting such a narrow slice of history is like trying to find a single page in a book that has already had most of its chapters ripped out. It's possible, but you need to know exactly where to look. One more wrinkle is that carbon anomalies don't last forever in a clean form. Over tens of millions of years, geological processes can blur, compress, or even erase the signals. Rocks metamorphose under pressure. Isotopic ratios get diluted as sediments mix and the clarity of the spike fades. This means that if a civilization left its mark 100 million years ago, the chances of us clearly recognizing it are much lower than if it happened, say, 5 million years ago. The older the event, the more it looks like noise against the backdrop of Earth's long carbon cycle. Still, the carbon footprint remains one of the most promising markers. It's not about skyscrapers or artifacts, it's about chemistry. Civilization is, in many ways, a large-scale process of moving carbon around, digging it up, burning it, and redistributing it into the air and water. That redistribution leaves a fingerprint that nature rarely produces so abruptly. If we ever did find a mysterious carbon isotope excursion that couldn't be explained by volcanism, asteroid impact, or methane release, we would have to seriously consider the possibility that it was technological in origin. For now, every anomaly we've studied seems to have a plausible, natural explanation. But the Silurian hypothesis doesn't require proof of a past civilization to be useful. It highlights the fact that our own carbon signature could one day be misinterpreted as natural, and that maybe some events we already call natural deserve a second look. It teaches us that the geological record is both rich in clues and treacherously ambiguous. If carbon signals are one of the clearest legacies civilizations can leave behind, then nuclear activity provides an even more distinctive marker. Unlike carbon shifts, which can be produced by natural processes such as volcanism or methane release, nuclear byproducts are almost entirely artificial. On Earth, there are very few naturally occurring isotopes beyond uranium and thorium, but industrial societies like ours generate elements and isotopes that simply don't appear in nature in detectable quantities. If those isotopes were found in rocks millions of years old, it would be nearly impossible to explain them without invoking a technological source. Consider plutonium-244. This isotope has a half-life of about 80 million years and does not naturally exist on Earth in measurable amounts today. It was present in trace levels during the formation of the solar system, but has long since decayed away. If geologists were to discover fresh deposits of plutonium-244 or other transuranic isotopes in rocks from the distant past, it would raise eyebrows. The only known processes capable of creating these isotopes are supernovae, neutron star mergers, or human-made nuclear reactors and weapons. Since we can usually identify whether material came from a cosmic event, finding a small but anomalous concentration in sediments could suggest nuclear technology. Modern nuclear power and weapons testing have already left such traces. During the mid-20th century, atmospheric nuclear testing spread fallout around the globe. This included isotopes like cesium-137 and strontium-90, both with half-lives long enough to linger in sediments for centuries to millennia. While these isotopes decay too quickly to survive deep time, they point to a principle. Once a civilization starts splitting atoms, the fingerprints are global and widespread. Even if no bombs were detonated, civilian nuclear reactors produce long-lived isotopes that can leak into the environment through accidents or waste disposal. Traces of iodine-129, for example, with a half-life of 15 million years, could theoretically persist in the rock record far longer than human civilization itself. Beyond nuclear material, industrial chemistry also leaves unique signals. Humans have manufactured an enormous range of synthetic compounds: chlorofluorocarbons, CFCs, persistent organic pollutants, pesticides, flame retardants, that did not exist on Earth before us. Some break down quickly, but others are remarkably stable. Even when the molecules themselves don't survive, the unusual ratios of elements they contain, chlorine, fluorine, or bromine in odd configurations, could leave subtle fingerprints in sediments. If another civilization had developed industrial chemistry, it's plausible they would have also produced unique synthetic compounds that left traces. Detecting them would be difficult, millions of years later, but not impossible. Metallurgy provides another angle. Industrial societies extract and refine metals in unnatural concentrations. Aluminum is the classic example. Though it makes up about 8% of Earth's crust, it is almost never found in metallic form because it bonds tightly with oxygen and silicon. Refining it requires immense energy. Humans now produce millions of tons of pure aluminum every year, scattering it into airplanes, vehicles, power lines, and packaging. If we disappeared, most of it would corrode over time, but certain deposits might remain buried in sediments. Geologists finding an unusual pocket of concentrated, refined aluminum in rocks millions of years old would face a puzzle. There is no natural process that should create it. The same is true for other refined metals and alloys: stainless steel, titanium alloys, and specialized magnetic materials. Even more subtle are isotope ratios in metals. Humans have altered the natural distribution of lead, for instance, through centuries of mining and smelting. The global lead cycle now bears our fingerprint, with isotope ratios shifted in ways that won't easily revert. Similarly, industrial copper and nickel mining leaves behind tailings that concentrate rare isotopes unnaturally. If another civilization engaged in similar activities, we might expect to see odd, localized anomalies in the isotopic record of heavy metals. One might argue that natural processes can mimic some of these signals. Volcanic eruptions, for example, concentrate heavy metals and scatter them globally. But volcanism produces distinctive patterns tied to magma chemistry, while industrial refinement produces sharp, localized concentrations that don't match volcanic deposits. The difference may be subtle, but it's detectable if you know what to look for. Another possible chemical fingerprint comes from fertilizers. Industrial agriculture consumes enormous amounts of nitrogen-based fertilizers, derived from the Haber-Bosch process, which pulls nitrogen from the air and fixes it into ammonia. This practice has doubled the amount of biologically available nitrogen on Earth in just a century. The result is a permanent alteration of the nitrogen cycle. Sediments laid down during this era carry unusual nitrogen isotope ratios. Over time, this anomaly will be locked into rocks. If another civilization farmed at a global scale, we might expect to see a similar disruption in nitrogen isotopes somewhere in the ancient record. The same logic applies to phosphorus. Industrial agriculture also spreads phosphorus fertilizers mined from specific deposits. Once released, phosphorus cycles into rivers, lakes, and oceans, creating dead zones and unusual sediment chemistry. If a pre-human civilization engaged in intensive agriculture, their legacy could include thin layers of phosphorus-rich sediments scattered across ancient deltas or seabeds. Altogether, nuclear isotopes, synthetic chemicals, unusual metal concentrations, and altered nutrient cycles form a suite of possible markers that civilizations can't help but leave behind. They are not as dramatic as buried ruins, but they are far harder to erase completely. The fact that humanity has already scattered these signals across the planet in just a few generations shows how powerful they are. If we want to ask whether Earth hosted another industrial society before us, these are the kinds of fingerprints we would have to search for, because they are the only ones with any real hope of surviving millions of years of geological change. When people think about what humanity will leave behind for the far future, plastics almost always come up. They're everywhere, in our oceans, in our soils, even in the air we breathe. They're durable, resistant to decay, and produced in mind-boggling quantities. Today, humans generate hundreds of millions of tons of plastic every year, much of which ends up scattered across the planet. It seems almost unthinkable that plastics wouldn't still be around, millions of years from now, silently marking our presence. But the truth is more complicated. Plastics do persist, but deep time is relentless, And their ultimate fate isn't as straightforward as most people imagine. Plastics are made from long chains of synthetic polymers derived from petroleum. These chains are very stable compared to most natural organic molecules, which is why plastic bottles, bags, and packaging can last for decades without breaking down. But plastics aren't indestructible. Sunlight, oxygen, and heat slowly degrade them, breaking the chains into smaller fragments. That's why most of the plastic in the oceans today doesn't look like intact bottles. It's microplastic, tiny particles worn down from larger pieces. These fragments then settle into sediments, becoming part of the geological record. Already, scientists have found microplastic particles embedded in layers of beach sand, river mud, and seafloor deposits. In some cases, plastics even fuse with natural materials. A striking example is plastiglomerate, a rock-like material where melted plastic mixes with sand, shells, and volcanic rock. This hybrid substance has already been documented on beaches in Hawaii and elsewhere. Unlike loose plastic, plastiglomerate is more geologically stable. It can be buried, compressed, and preserved like any other sedimentary rock. Future geologists may find plastiglomerate layers marking the Anthropocene, much the way we now use volcanic ash layers to date ancient events. The question is how long these traces can last. On human timescales, plastic feels permanent, but millions of years of heat, pressure, and chemical transformation change the picture. Plastics are organic compounds, and under the right conditions, they can break down into hydrocarbons. In other words, if buried deeply enough, plastics could eventually revert into something resembling oil or natural gas. That means their direct signature may vanish, replaced by indirect chemical residues. The chance of finding a recognizable plastic bottle 100 million years from now is essentially zero. But the chance of detecting anomalous hydrocarbon layers or odd carbon-hydrogen ratios created by degraded plastics is higher. It's worth noting that our plastic signal is already global. Microplastics have been detected in the Arctic snow, the Mariana Trench, and even inside human bodies. They've entered the food chain and are cycling through ecosystems worldwide. This ubiquity increases the odds that some fraction of them will survive in sediments that eventually lithify into rock. Even if most break down, a trace amount could persist long enough to confuse or intrigue whoever might be studying the rocks in the distant future. If another civilization had produced plastics or similar synthetic polymers, we might expect to see comparable markers in the deep past. Thin layers of unusual carbon-rich particles could appear in sediment cores, distinct from natural organic matter. Strange hybrid materials like plastiglomerate might also form. The challenge, as always, is distinguishing these signals from natural processes. A sudden influx of organic material into sediments could easily be explained by algal blooms, wildfires, or natural petroleum seeps. Unless the chemical structures were extremely distinctive, ancient plastics might blur into the background noise of Earth's carbon cycle. Another factor is scale. Humans have transformed the surface of the planet in just a century, producing more plastic than the total weight of all living animals combined. If a prior civilization was smaller or shorter lived, their plastic footprint might have been modest, too small to stand out clearly in the record. That means the absence of evidence doesn't prove they weren't there. It may only reflect the limits of how much material can survive the brutal editing of geological time. Still, plastics remain one of the most likely technofossils of our age. They are novel, widespread, and unlike almost anything produced by natural processes. Their survival over millions of years is uncertain, but at least some traces are likely to persist. For future scientists, finding plastiglomerate or microplastic residues in sediments would be a strong clue that a technological species once lived here. And by extension, if we ever find similar anomalies in ancient rocks, it would raise the unsettling possibility that Earth has already hosted more than one civilization. One of the most striking conclusions of the Silurian Hypothesis is that Earth itself may not be the best place to look for signs of an earlier civilization. Our planet is active and restless. Its surface is constantly recycled through plate tectonics, weathering, and erosion. Over tens or hundreds of millions of years, even the strongest materials can be destroyed or transformed beyond recognition. If you wanted to leave a permanent record of your existence, Earth would actually be a poor choice. But there are other places in the solar system that are far better at preserving history. Take the Moon. Unlike Earth, it has no atmosphere, no plate tectonics, no weather, and almost no erosion. Surface features can remain intact for billions of years. Apollo astronauts left footprints in the lunar dust more than 50 years ago, and those footprints could still be visible millions of years from now. If a previous civilization had explored or colonized the moon, their artifacts might still be sitting on the surface, eroded only by micrometeorite impacts. A buried structure shielded under regolith could survive even longer. In terms of preservation, the moon is one of the best time capsules in the solar system. Mars offers another intriguing possibility. Although it once had rivers, lakes, and perhaps even oceans, it lost most of its atmosphere billions of years ago. Since then, its surface has been relatively stable, with no plate tectonics to recycle crust into the mantle. Ancient riverbeds and lake basins are still visible today, dating back billions of years. If an advanced species ever existed on Earth and travelled to Mars, traces of their presence might still be detectable, perhaps as unusual artifacts, mining scars, or refined materials buried beneath the dust. Even if they never went to Mars, searching there for technological traces provides a useful comparison. If Earth tends to erase evidence, but Mars does not, then studying both helps us understand what signs of civilization look like in different environments. Asteroids and other small bodies in the solar system could also hold clues. Mining asteroids is often imagined as a logical step for an advanced society seeking resources. Unlike Earth, asteroids don't have erosion or tectonic recycling. Excavation scars or unnatural mineral distributions could potentially survive for billions of years. Of course, detecting them would require careful surveys, and distinguishing natural geological processes from industrial activity would not be easy. Still, the preservation potential is far higher than on Earth. This broader perspective shows why Frank and Schmidt link the Silurian Hypothesis to astrobiology. If we're trying to detect civilizations on exoplanets, we can't just assume they'll leave behind radio signals or orbiting satellites. Civilizations may rise and fall, leaving only subtle geological or chemical traces. By thinking about where to look for long-lasting evidence in our own solar system, we learn how to design better strategies for looking elsewhere. If Earth buries its history, maybe we need to think about other planets and moons as the archives of intelligence. There's also a cautionary element here. If another civilization had reached space, the Moon or Mars might still bear their fingerprints. The fact that we haven't found anything so far suggests either that no such civilization existed, or that their reach never extended beyond Earth. In either case, it's a reminder of how fragile technological species may be. Even if intelligence arises, it might not last long enough to spread beyond its homeworld. That thought has direct implications for us. If we want our own civilization to endure, we may need to look outward, not just for survival, but for permanence. Searching beyond Earth also highlights how differently time behaves across environments. A city on Earth is doomed to collapse and vanish in a few tens of thousands of years at most. But an artifact on the Moon could last 100 million years. A probe in orbit around the Sun, far from planetary bodies, might circle undisturbed for billions. If we want to imagine how a civilization could leave behind a true monument to its existence, space, not Earth, is the logical place. This is one of the most profound insights the Silurian Hypothesis offers. It shows us that Earth may not be the full story. If there ever were predecessors, and if they were advanced enough to explore beyond their homeworld, the most likely place to find their traces isn't buried in Earth's crust, but lying quietly on the airless plains of the Moon, or under the rust-coloured dust of Mars. And even if the answer is no, this way of thinking prepares us for the day when we might study exoplanets with enough detail to search for the long-faded echoes of civilizations that are no longer there. Whenever the idea of a pre-human civilization comes up, it inevitably attracts comparisons to so-called out-of-place artifacts, or OOP arts. These are objects claimed to be too advanced, too old, or simply inexplicable within mainstream archaeology and geology. Over the years, people have pointed to iron nails found in coal seams, strange metallic spheres from South Africa, or fossilized hammers embedded in stone as supposed proof that advanced beings walked the earth long before recorded history. These stories are compelling, but almost none survive serious scientific scrutiny. Most of these artifacts turn out to have ordinary explanations once studied carefully. Coal seams, for example, form over millions of years, but they can also be intruded by cracks and voids, where more recent objects slip in. An old nail, washed into a crack, can end up encased in coal deposits that look ancient, even though the object itself is only centuries old. The famous London hammer, a hammerhead encased in a nodule of rock, was likely just an iron tool from the 19th century surrounded by concretion, hardened minerals that can form in decades, not millions of years. The so-called Klerksdorp spheres from South Africa, sometimes touted as artificial, are actually natural concretions formed by sedimentary and volcanic processes. The persistence of these claims highlights two things. First, humans are fascinated by the idea that we aren't the first. There's something deeply appealing about the thought of a forgotten cycle of civilizations, wiped from memory, but leaving tantalizing fragments. Second, the real science of the Silurian hypothesis has to be careful to distinguish itself from pseudoscience. Frank and Schmidt were explicit. They weren't suggesting that OOP arts are genuine or that there's evidence of ancient industrial empires. Their point was that even if such a thing had existed, the likelihood of us finding hammers, coins, or statues from it is almost zero. The real evidence, if it exists, would be buried in isotopes, sediments, and chemical anomalies, not in sensational artifacts. Still, these misinterpretations serve a purpose. They show how easy it is to mistake natural formations for artificial ones, especially when we want the story to be true. A rounded stone can look like a manufactured ball, mineral veins can mimic metal wires, and erosion can create patterns that resemble carvings. Our brains are wired to see intentional design, sometimes where none exists. This is why archaeologists and geologists apply strict criteria before labelling something an artifact. Provenance, dating, and context matter. Without them, a curious rock is just a rock. There's also the cultural layer. Stories of lost civilizations are embedded in myth and legend around the world. From Plato's tale of Atlantis to Hindu epics describing cycles of creation and destruction, people have long imagined worlds before our own. These stories resonate because they express a truth we feel instinctively. Civilizations are fragile, time is vast, and we are not as permanent as we might think. But myths and legends aren't evidence. The Silurian hypothesis draws a hard line. It asks what physical signatures would truly survive in the geological record, rather than leaning on folklore or anecdotes. By separating scientific reasoning from misinterpretation, we gain clarity. If there really had been an industrial society before humans, we wouldn't find its tools lying around intact. Instead, we'd be forced to read the story from the rocks themselves. That means carbon anomalies, isotopic oddities, strange sedimentary layers, or unusual concentrations of metals. Anything else, a hammer in a coal seam, a metallic sphere in sandstone, almost certainly belongs to the long list of natural processes that can fool the eye but not careful analysis. Ironically, this distinction makes the Silurian hypothesis more powerful. It shows that science doesn't need sensational artifacts to ask provocative questions. By grounding the discussion in chemistry, geology, and climate records, the hypothesis avoids the traps of pseudoscience while still engaging with the same human curiosity that drives legends of lost civilizations. It takes the allure of Atlantis and OOP arts and channels it into a serious, testable framework. That's why scientists take it seriously. Not because they believe there really were ancient industrial empires, but because the question itself forces us to sharpen our tools for detecting civilization in deep time. One of the biggest challenges with the Silurian hypothesis is that nature itself often creates signals that look suspiciously like the fingerprints of civilization. If we find a sudden shift in carbon isotopes, an unusual concentration of metals, or a rapid climate change event, the temptation is to wonder whether something technological caused it. But in most cases, natural processes are more than capable of producing the same effects. This overlap is what makes the search for ancient civilizations so difficult. It's not that we lack anomalies in the record, it's that almost all of them have plausible natural explanations. Take the Paleocene-Eocene thermal maximum, or PETM, about 56 million years ago. During this event, global temperatures spiked by 5 to 8 degrees Celsius, oceans acidified, and ecosystems around the world shifted dramatically. The geological record shows a sharp carbon isotope anomaly during this time, indicating a massive injection of carbon into the atmosphere. To a geologist millions of years in the future, it might look exactly like what humans are doing now. rapid carbon release, warming, and ecosystem disruption. But most scientists believe the PETM was caused by natural processes, possibly volcanic activity, methane hydrate release, or a combination of both. There is no need to invoke an industrial civilization to explain it. Volcanism is especially important here. Large igneous provinces, or LIPS, are regions where enormous volumes of lava erupted in a geologically short time. These events release massive amounts of carbon dioxide and sulfur into the atmosphere, altering global climate. The Siberian Traps eruption around 252 million years ago is thought to have driven the Great Dying, the largest mass extinction in Earth's history. Again, the chemical and isotopic signals left behind resemble the kinds of disruptions we might expect from a global industrial society, but they were entirely natural. Asteroid impacts can also mimic civilization signals. When the Chicxulub impact struck 66 million years ago, it released not only shockwaves and tsunamis, but also vast amounts of vaporized rock and carbon into the atmosphere. The thin layer of iridium-rich clay that marks this event worldwide is the classic example of a sharp, global chemical anomaly. If we didn't know about the impact, we might see that layer and wonder whether some technological process could explain it. In this case, the evidence of a crater and shocked minerals resolves the mystery, but it illustrates the point. Sudden global chemical shifts don't necessarily mean civilizations. Even biological processes can create misleading signals. For example, massive algal blooms in the oceans can lead to oxygen depletion, creating dead zones that accumulate organic-rich sediments. These events can lock away unusual concentrations of carbon, phosphorus, and nitrogen in the rocks. From a distance, they might look like the byproducts of large-scale agriculture or industry. Similarly, the rise of land plants hundreds of millions of years ago fundamentally altered Earth's atmosphere, leaving a lasting isotopic signature that could easily be misinterpreted if we didn't know the biological cause. Another complicating factor is that some of these natural events are both abrupt and short-lived, just like technological disturbances. The PETM, for instance, lasted about 200,000 years, long in human terms, but a blink in geological time. In the rock record, it appears as a relatively thin layer sandwiched between millions of years of stability. A short-lived industrial civilization might leave a layer of similar thickness. Without clear markers like synthetic chemicals or transuranic isotopes, it becomes nearly impossible to distinguish between natural and technological origins. This is why Frank and Schmidt stressed that the Silurian hypothesis isn't about proving past civilizations. It's about acknowledging how ambiguous the geological record can be. We already see events that look very much like industrial disturbances. They are almost certainly natural, but they remind us that if a civilization had once existed, its traces could easily be misclassified as just another volcanic burst, methane release, or extinction pulse. The overlap between natural and artificial signals also matters for astrobiology. When we look at exoplanets, we may one day detect atmospheric anomalies or rapid climate shifts. The first question will always be, is this natural, or is it evidence of technology? By grappling with that same uncertainty on Earth, we prepare ourselves for interpreting distant worlds. In a way, the PETM and other events are rehearsal cases. They show us what ambiguous signals look like, and how easily we can be misled by natural phenomena. In the end, the fact that natural processes can mimic civilization signatures cuts both ways. On the one hand, it makes the Silurian hypothesis harder to test because we can never fully rule out natural explanations. On the other hand, it means that civilizations may not stand out as much as we assume. Even if we leave behind a carbon spike, a chemical oddity, or a thin layer of plastics and metals, it may one day blend seamlessly into the long record of volcanic eruptions, impacts, and natural climate shifts. That sobering thought underscores the fragility of our legacy, and the difficulty of ever knowing with certainty whether we were truly the first. For all its intrigue, the Silurian hypothesis faces serious objections, and most scientists remain highly skeptical that any pre-human civilization ever existed. The reasons aren't just about the absence of direct evidence, but about how evolution, biology, and geology work together to make such a scenario unlikely. Understanding these objections helps clarify why the idea is framed as a thought experiment rather than a real claim about Earth's past. The first and most obvious objection is the lack of fossils. Fossilization is rare, but it isn't so rare that we should expect zero evidence of a tool-using, large-brained species if one had existed for millions of years. Dinosaurs dominated the planet for more than 150 million years, and we have fossils of everything from their teeth and claws to their skin impressions and even their nests. If a species capable of building cities or crafting technology had lived during that time, or in any other window of Earth's history, we would expect at least some fossil traces of unusual anatomy. An industrial civilization almost certainly requires manipulative limbs, complex nervous systems, and large brain cases. So far, no fossils with these features have turned up outside the hominin lineage. That doesn't rule it out absolutely, but it makes it very unlikely. A related objection is the evolutionary pathway itself. Intelligence on the human level is extraordinarily rare. Life has existed for billions of years, and yet only one lineage, ours, has produced an industrial civilization. Dinosaurs, mammals, and countless other groups thrived for tens of millions of years without evolving the kind of intelligence needed for technology. Even within our own family tree, dozens of hominin species lived and died before Homo sapiens, and only we developed complex language and industry. This suggests that intelligence is not an inevitable outcome of evolution, but rather a rare and fragile convergence of circumstances. Expecting it to have happened twice on the same planet stretches probability. Another objection comes from timescale. Our own civilization has existed for only about 2 centuries in its industrial form. That's a blink compared to the age of Earth. If a prior civilization had existed, it would need to have arisen, developed industry, and then collapsed in a similarly narrow window. The odds of 2 civilizations, separated by millions of years, both appearing in those tiny slices of time, are extremely low. This doesn't make it impossible, but it makes it an unlikely pattern to repeat. Then there is the matter of technosignatures. As discussed earlier, a civilization should leave behind distinctive chemical footprints, synthetic isotopes, unusual alloys, altered nutrient cycles. So far, nothing in the rock record demands a technological explanation. Every anomaly we've studied, whether carbon isotope excursions, mass extinctions, or metal concentrations, has plausible natural causes. Without unambiguous markers like transuranic isotopes or plastics in deep time, there's no reason to invoke civilizations as explanations. Another objection deals with survivability. If a civilization reached the point of industry, why didn't it last longer? Humans are already exploring space and could, in principle, establish a presence beyond Earth within the next few centuries. Once a species spreads to other planets, it becomes much harder to erase completely. If there had been an advanced civilization before us, why don't we see traces on the Moon, Mars, or asteroids? The silence of our own solar system argues strongly against the existence of any previous spacefaring society. Some scientists also raise a statistical argument, the rare Earth hypothesis. This idea suggests that the combination of conditions needed for complex, intelligent life is extraordinarily unlikely. The right planet, the right atmosphere, the right evolutionary pressures, the right catastrophes at the right times, all of these have to align. By this reasoning, Earth may not just be rare in the universe, but rare even within its own history. The fact that one industrial civilization arose at all is remarkable, but expecting a second is perhaps asking too much. Finally, there's the burden of proof. Extraordinary claims require extraordinary evidence. The Silurian Hypothesis suggests something extraordinary, that Earth might have hosted another industrial society long before us. Without clear direct evidence, the simplest explanation remains that humans are the first. This principle of parsimony, often called Occam's razor, guides scientific thinking. We don't multiply explanations without necessity. Since natural processes explain the anomalies we see, there is no scientific need to propose vanished civilizations to account for them. These objections don't make the hypothesis meaningless. They're exactly why Frank and Schmidt framed it as an exercise rather than a claim. By laying out the reasons it's unlikely, they highlighted the limits of what we can detect and the assumptions we carry about uniqueness. But as a real description of Earth's past, the Silurian Hypothesis runs into hard walls. No fossils, no unambiguous technosignatures, and no evidence beyond natural explanations. For now, the scientific consensus is clear. We are the first industrial civilization on this planet. The real value of the hypothesis isn't in proving otherwise, but in reminding us how fragile evidence is, how rare intelligence may be, and how uncertain our long-term legacy will become. Despite the many objections to the Silurian hypothesis, there is one counterpoint that keeps the conversation alive. Intelligence has appeared in more than one form on Earth. Humans are the only species to build a global, industrial civilization. But we are not the only species with complex cognition, problem-solving, and even tool use. The existence of other intelligent animals doesn't prove that there was a civilization before us. But it does remind us that intelligence isn't uniquely tied to humans. It's something evolution has tested more than once. Take octopuses. With nervous systems spread through their arms and astonishing problem-solving skills, they are often considered the most intelligent invertebrates on Earth. They can open jars, escape enclosures, use tools like coconut shells for shelter, and even demonstrate play behaviour. Their intelligence is so alien compared to ours that some scientists describe them as the closest thing to encountering a mind from another planet. If conditions had been different, say, if cephalopods had evolved in a more stable environment instead of oceans prone to repeated upheavals, could they have developed in ways that went beyond survival, into culture and technology? It's speculative, but not inconceivable. Birds also provide compelling examples. Corvids, such as crows and ravens, have demonstrated remarkable intelligence. They use tools, solve puzzles, and even appear to understand cause and effect relationships that rival those of young human children. Some species pass knowledge across generations, teaching their young how to bend twigs into hooks or use cars to crack nuts on roads. Parrots, with their memory and capacity for vocal mimicry, show another dimension of intelligence, communication that borders on language. If we judge intelligence by problem-solving, adaptation, and social learning, then birds come surprisingly close to the traits we consider uniquely human. Marine mammals push the boundary further. Dolphins use cooperative hunting strategies, communicate with distinct vocal signals, and even pass learned behaviours within groups. There are documented cases of dolphins teaching each other how to use sponges to protect their snouts while foraging, essentially a form of tool used passed culturally rather than genetically. Whales too have complex social structures and songs that may function as cultural traditions. What these examples show is that intelligence is not a one-off miracle. It has evolved independently in different branches of life: mammals, birds, cephalopods. None of these lineages has developed industrial civilization, but they demonstrate that nature is willing to experiment with advanced cognition. Intelligence, in other words, might not be unique. It might be a recurring possibility, even if the full leap to technology is rare. This matters for the Silurian hypothesis because it softens one of the strongest objections, that it is improbable for intelligence to have evolved twice. If we already see multiple origins of intelligence at smaller scales, then the leap to say it could, under the right conditions, reach industrial levels more than once is not unthinkable. Dinosaurs, for example, included species like Troodon, with relatively large brains for their body size. Some paleontologists have speculated that had the asteroid not struck 66 million years ago, certain dinosaur lineages might have continued along a trajectory toward greater intelligence. While speculative, it suggests that evolutionary pathways toward higher cognition are not completely unique to mammals. There's another angle worth considering. Intelligence doesn't have to look like ours. We often imagine civilizations as human-like, creatures building cities, making tools, burning fuels. But what if intelligence manifested differently? An aquatic civilization, for instance, would have fewer opportunities to use fire or metal, but might have found other ways to manipulate their environment. A species with communication far richer than ours might have developed culture without material technology. If we limit our definition of civilization to machines and skyscrapers, we may overlook other forms of advanced societies that leave subtler traces. This ties into a broader question about how we even define civilization. Is it industry, or is it the ability to shape and transmit culture across generations? Some argue that certain animal societies already meet part of that definition. The difference is scale. Human intelligence produced global transformation, while dolphin or crow intelligence remains localized. But the boundary between the two is thinner than we like to think. If intelligence isn't unique, then the Silurian hypothesis becomes less about probability and more about evidence. The idea that another species could have reached industrial levels is still unlikely, but not impossible. Evolution has shown that cognition arises in multiple ways. The real challenge is not whether it could happen, but whether we could detect it after it has vanished. If octopuses had somehow developed an industrial society 100 million years ago, would we find its traces today? Probably only in subtle chemical and geological anomalies, the same markers we're leaving now. In the end, the existence of multiple intelligent species on Earth today doesn't prove there was a civilization before us, but it keeps the door open. It reminds us that evolution is inventive, intelligence is not confined to one lineage, and the story of life is full of surprises. If we are the first industrial civilization, it might be by chance as much as by inevitability. And if intelligence isn't unique, then perhaps Earth's deep past contains more mysteries than we currently allow ourselves to imagine. When thinking about whether another civilization might have existed long before us, a natural step is to ask what kind of evidence we ourselves will leave behind. If humanity disappeared tomorrow, how long would our presence be visible in the geological record? Would another species, millions of years from now, be able to reconstruct our story? Or would our entire existence shrink to a thin, ambiguous layer in the rocks? This isn't just speculation about the future. It's the closest analogy we have for testing the Silurian Hypothesis. In the immediate centuries after our disappearance, the signs would be obvious. Our cities would still stand, albeit decaying rapidly. Concrete buildings would begin to crack, bridges would collapse, steel would corrode, and glass would shatter. Forests would reclaim roads, farms would vanish under new vegetation, and eventually, much of the built world would collapse into rubble. Within 10,000 years, almost every surface structure we've built would be gone, buried, or unrecognizable. Even the largest monuments would not last. The Great Pyramids or Mount Rushmore, often imagined as eternal, would be weathered into unremarkable mounds of stone. The longest-lasting physical traces on the surface might be things like underground tunnels, mines, or waste storage sites. But if we zoom out to geological timescales, physical structures matter far less than chemical footprints. In 1 million years, cities themselves would be erased, but sediments would still carry the markers of our activity. Plastics, metals, and industrial chemicals would be embedded in layers of rock. Microplastics already litter oceans and soils, and some of these will settle into sedimentary deposits that, under the right conditions, could persist for millions of years. Plastiglomerates, fused mixtures of plastic and natural materials, might also survive as distinctive technofossils. Carbon is another enduring signal. Our fossil fuel emissions have sharply altered the carbon isotope ratio in the atmosphere and oceans, a shift that is now locking into sediments. This anomaly, known as the Suez effect, will remain detectable long after the last smokestack has rusted away. Millions of years from now, geologists examining rock cores will see an abrupt spike in carbon-12 levels, alongside evidence of rapid warming and mass extinction. This Anthropocene layer may be one of our most enduring legacies. Then there are radioactive isotopes. Atmospheric nuclear testing in the 20th century spread isotopes like cesium-137 and strontium-90 across the globe, leaving a thin but unmistakable marker. These isotopes have relatively short half-lives, so they won't survive millions of years, but other byproducts of nuclear reactors and weapons might. Isotopes like iodine-129, with a half-life of 15 million years, or plutonium-244, with a half-life of 80 million years, could persist in small amounts within sediments. For a future geologist, finding such isotopes in an otherwise ordinary rock layer would be a smoking gun for technological activity. Industrial metals also tell a story. We have refined and redistributed enormous amounts of aluminum, copper, and steel. While most of it will corrode, certain deposits may fossilize in ways that stand out geochemically. The same goes for fertilizers. Our agricultural practices have doubled the amount of reactive nitrogen on Earth and redistributed phosphorus on a massive scale. These changes are altering sediment chemistry in ways that will persist as odd signatures for millions of years. So how long will we remain detectable? On the order of tens of millions of years, many of these markers will still be visible. By then, tectonics will have begun to recycle some of the crust, but younger layers should preserve the Anthropocene clearly. In 100 million years, the record will be thinner, patchier, and more ambiguous, but traces of carbon anomalies, unusual isotopes, and altered sediments could still be identified. Beyond 500 million years, however, the odds diminish drastically. By then, most of Earth's surface will have been recycled through tectonics or transformed by metamorphism. Whatever remains of our signal would be fragmentary at best and may blend indistinguishably with natural events like volcanic carbon releases or impact-driven extinctions. This exercise shows why the Silurian hypothesis is so slippery. If another industrial society had existed 10 million years ago, we might still be able to detect faint evidence of it. If it lived 100 million years ago, the evidence would be much harder to interpret. And beyond that, it might vanish almost entirely. Our own existence demonstrates the point. We are global, we are transformative, and yet our entire geological footprint may one day look like a few curious anomalies tucked into a thin band of rock. The unsettling implication is that being visible to the far future doesn't require monumental ruins or spacecraft. It requires only that a species leave behind chemical disruptions large enough to register in the rock cycle. Humanity is certainly doing that, but our legacy may not be the grand monuments we imagine. It may be a thin, strange layer of plastic dust, isotopes and altered sediments that future geologists debate endlessly. And if that's true for us, then it could have been true for anyone who came before. When we think about civilizations, we imagine permanence. Cities, monuments, and technologies feel like they should stand forever, anchoring us in history. But if Earth teaches us anything, it's that permanence is an illusion. Civilizations can rise, dominate for a brief span, and then vanish so completely that, given enough time, even the memory of their existence is erased. This is where the Silurian hypothesis forces us to face a sobering truth. Not only could an earlier industrial society disappear without a trace, but ours could too. Consider how fragile civilizations have been throughout human history. The Roman Empire lasted for centuries, stretching across continents, yet today its ruins are fragments. Mayan cities, once bustling with tens of thousands of people, were swallowed by jungle until rediscovered. In both cases, collapse came long before the stones themselves had worn away. Multiply that by millions of years, and the ruins don't just fade, they are pulverized, buried, melted, or consumed by the Earth's shifting crust. If humanity were to end suddenly, through war, disease, climate collapse, or any of the countless risks that stalk our future, our most visible achievements would fade within millennia. Skyscrapers would collapse, satellites would fall, and roads would crumble. Within 1,000,000 years, the surface of the planet would carry no obvious signs that cities ever existed. The only hints would lie buried in the sediments. Strange chemical signals, anomalous isotope ratios, and thin, peculiar layers of debris. To a future species digging through the rocks, those hints might look no different from countless natural catastrophes already recorded in Earth's history. This is why vanishing without a trace is not just possible, it may be the default. Earth is not a museum, preserving artifacts forever. It is a dynamic, restless system that recycles, reshapes, and erases. Tectonic plates drag the crust back into the mantle. Mountains rise and erode away. Oceans open and close. In 100 million years, the continents will have shifted again, and much of today's land may be underwater or crushed into new mountain ranges. Whatever faint signal of humanity remains will be scattered and obscured. The same forces apply backward in time. If another civilization had existed before us, say 10 or 100 million years ago, its traces would have faced the same relentless erasure. The odds of finding preserved structures or intact artifacts are vanishingly small. Even fossils of living species, which form far more easily than cultural artifacts, are rare. If entire lineages of animals can disappear from the record, it's easy to imagine how an industrial society, short-lived and localized, might vanish as well. And that is the paradox of civilizations in deep time. The more advanced a society becomes, the faster it consumes resources and destabilizes its environment. This makes collapse more likely. Yet the very processes of collapse, climate disruption, extinctions, chemical shifts, are the same ones that nature produces on its own. That means the final geological record of a civilization is likely to be thin, ambiguous, and easily misread. A spike in carbon could be industry or volcanism. An odd isotope could be technology or a rare geologic quirk. Unless a marker is unmistakably artificial, the traces blend into Earth's background noise. This possibility carries a humbling lesson for us. We often assume our civilization will be remembered forever, carved into monuments or preserved in records. But deep time does not keep records in the way we imagine. The Earth erases. If another species comes after us in 50 million years, it may know nothing of our cities, cultures, or achievements. At best, it may puzzle over a thin layer of rock marked by plastic dust, chemical anomalies, and a mass extinction. The rest will be silence. This risk of vanishing without a trace isn't just a thought experiment about others who might have come before us. It is also a mirror for ourselves. It forces us to confront how fragile our presence really is, and how easily even the mightiest of civilizations can be reduced to ambiguity in the endless churn of geological time. One of the reasons scientists take the Silurian hypothesis seriously, even if they don't believe an earlier civilization existed, is because of what it teaches us about searching for life elsewhere. Astrobiology, the study of life in the universe, depends on our ability to detect signals of biology or technology on other planets. If Earth itself can erase most evidence of an industrial society in just a few million years, then the challenge of finding civilizations on exoplanets becomes far greater than we often assume. Right now, the search for extraterrestrial intelligence, SETI, focuses heavily on radio signals. The logic is simple. Advanced societies might communicate with radio waves, and those waves can travel across interstellar distances. But this approach assumes we are looking at civilizations in real time while they are still active. The Silurian hypothesis highlights the limitation of that approach. If industrial societies tend to be short-lived, rising, burning brightly, and then collapsing, the odds of two civilizations overlapping in time are slim. The more realistic question may not be, are they broadcasting now? But what traces did they leave behind, and how long do those traces last? That shifts the focus from immediate techno-signatures, like radio waves or laser pulses, to long-lived ones. On Earth, the clearest long-term markers of civilization are chemical disruptions. Altered isotope ratios, synthetic compounds, radioactive residues, and technofossils like plastics. The challenge is that most of these signatures fade or become ambiguous after tens of millions of years. If we struggle to detect a potential civilization on our own planet's past, then detecting one on a distant world is even harder. This doesn't make the search hopeless, it just reframes it. For example, astronomers studying exoplanet atmospheres with future telescopes may detect gases that look out of balance. High levels of carbon dioxide paired with unusual pollutants, or oxygen levels that don't fit the geological context. These anomalies could, in principle, suggest industrial activity. But as the PETM and other events remind us, natural processes can create similar imbalances. To avoid false positives, we need to refine our understanding of how civilization-like signals can arise naturally. That's exactly the kind of insight the Silurian hypothesis forces us to develop. Another implication concerns planetary habitability. Earth has been habitable for billions of years, long enough for multiple cycles of civilization if intelligence were common. If we find that Earth only produced one industrial society in all that time, it strengthens the argument that intelligence is rare. If, on the other hand, evidence emerged that another civilization did exist before us, it would suggest that intelligence is repeatable and perhaps more common in the universe than we think. In either case, Earth becomes a crucial case study for estimating how often civilizations arise elsewhere. The hypothesis also highlights the importance of planetary environments beyond Earth. If civilizations want to leave a permanent mark, they may need to move beyond their homeworld. On Earth, tectonics and erosion erase the record. On the Moon or Mars, the record might persist indefinitely. That means that if extraterrestrial civilizations reach space, their traces might be more easily detected on airless moons, stable planets, or even in artificial objects left in orbit. Astrobiologists now consider not just the biosignatures of life, but also the potential for technosignatures that survive long after a civilization has gone extinct. This perspective adds urgency to our own situation. If we remain confined to Earth, our traces may fade into ambiguity in deep time. But if we spread beyond Earth, establishing a lasting presence on the Moon, Mars, or even in orbit, we increase the odds that our existence will be visible for millions or billions of years. In that sense, space exploration isn't just about survival, it's also about permanence, about ensuring that our story doesn't vanish as completely as those we wonder about in Earth's past. Ultimately, the Silurian hypothesis makes astrobiology harder but also richer. It warns us that civilizations may be far more difficult to detect than we once imagined. They may flare into existence, alter their planet for a short while, and then vanish, leaving only faint and ambiguous echoes in geology. If that's true, then the silence we hear when we scan the skies may not mean we are alone. It may only mean that the others are gone, erased by time, their legacies buried as thoroughly as ours will one day be. The Silurian hypothesis was never really about proving that another industrial civilization existed before humans. It was designed as a tool for thinking, an experiment to stretch the way we approach evidence, timescales, and the limits of knowledge. By asking, what if we are not the first? It forces us to see how fragile our assumptions really are. The first lesson is humility. We like to imagine ourselves as the inevitable product of evolution, the rightful heirs to Earth after billions of years of trial and error. But our place in history is razor-thin. We've only had industrial technology for 2 centuries, and our entire species for less than 500,000 years. That's not even a blink compared to the planet's 4.5 billion years. When you zoom out that far, the idea that we're unique and unrepeatable starts to feel less like a certainty and more like a comforting story we tell ourselves. Even if there never was a civilization before us, the hypothesis forces us to acknowledge that our dominance is temporary and precarious. The second lesson is about the nature of evidence. We tend to think of the past as knowable because we study fossils, rocks, and ruins. But the deeper we look, the more incomplete the record becomes. Most species leave no fossils. Most events leave no lasting marks. Entire landscapes are ground away, recycled, and rebuilt. What remains are fragments, and even those can be misleading. The Silurian hypothesis reminds us that absence of evidence is not always evidence of absence. Just because we don't see something doesn't mean it never happened. Time itself is a ruthless censor. A third lesson is about perspective. We often define civilization by its artifacts, buildings, machines, art, tools. But in the geological record, what really endures is chemistry. Altered isotope ratios, synthetic compounds, unusual mineral distributions. If that's what survives of us, then that's all that might have survived of anyone else. Civilization, stripped of its monuments and stories, reduces to a thin layer of odd chemistry in the rocks. That perspective reshapes how we think about our legacy. The things we imagine as permanent, the Great Wall, skyscrapers, satellites, are fleeting compared to a carbon isotope anomaly or a radioactive fingerprint. The final lesson is existential. If civilizations are short-lived and their traces fragile, then the universe may be full of stories that have already ended. Maybe other planets saw their own industrial ages rise and collapse, leaving behind faint scars that no one is around to interpret. Maybe intelligence is common, but survival is rare. If so, then our silence in the cosmos isn't because no one else was ever there. It's because they've already come and gone, and that possibility should sharpen how we see our own future. The Silurian hypothesis, at its heart, isn't about proving or disproving ancient civilizations. It's about asking how we would even know if one had existed. It challenges us to confront the limits of our tools, the biases of our thinking, and the staggering depth of time. Whether or not Earth has hosted more than one civilization, the exercise changes the way we see ourselves. Fragile, fleeting, and not nearly as permanent as we might like to believe.